was fueled by the development of differential privacy. And in my PhD, I applied differential privacy in different stages of an analyst that deals with data, let's say data collection, data targeting, et cetera, et cetera. And now this is one of my projects that came out of the PhD and I'm still working on. And I'm curious to hear your feedback on. And it's important to note that this is work together with Tom Boot. He's from the University of Groningen. Jaap Wieringa is also from the University of Groningen. And Thomas is from the University of Vienna. And I have a notebook that you can already open and that we will get into in this presentation. Oh yeah, I can click with this click. So to start with this presentation, I would like to imagine you three customers. So the first customer is me. Coincidentally, the second customer is Thomas from Vienna. And the third customer is Tom from Groningen. And Thomas, note, not the others, he's looking on Instagram and he sees an ad. So this is the ad that he is seeing. And he goes to the website, so he clicks on the ad, and he thinks, oh, that's a nice jacket, so let me order it on the website, and then he spends 200 euros. So to summarize this whole situation is that we have a bunch of customers. So we have Gilian, Thomas, and Tom, and they are, they have a couple of features. I am from Rotterdam, or I live now in Rotterdam, in Vienna and in Groningen, and we see that Thomas is treated and the others are not. So we only observe the profit for what we did. So we only observe for Gilian the profit without the ad. For Thomas, we observe the profit with the ad. And for Tom, we observe the profit without the ad. And now the challenge is, as you may know, that we want to kind of impute these numbers. So that we want to get the profit for the treated, for Gilian and for Tom. And that we want to get the profit if Thomas would have not seen the ad. Right? That's kind of the struggle here with targeting. Okay. And then the end goal is to kind of to get these numbers. And let's say we have these numbers. We can do this with all kinds of methods that you may have seen at this conference or that you can find online. And then we can essentially calculate the uplift. And this uplift represents what does the customer spend based on this ad. So in this case, Gilian, he spends. I spent 400 if I would have seen the ad, and I spent 400 when I didn't see the ad. So in my case, there's no point in showing me the ad because I have zero uplift, or the CATE is also what we call it sometimes. But we see that Thomas, this is a bit more attractive, right? He has 100 euros of profit, so we want to target Thomas and Tom, who has 90 euros, and then we want maximizing profit. Good. And usually what we see in the literature or in practice is that we want to learn a function that maps these features. So, this is just an example of these features, but you might have all kinds of features like age, etc., or behavior. And we want to map this directly to this uplift. So we don't want to do this imputation problem, but directly learn the treatment effect function. That's what we usually call it. And this is, this can be a simple model fit, or, you can use any method that you would like. And you can learn these features. You can learn the function that maps these features onto the uplift. Okay. And then the goal in practice is, at least that's what I'm assuming, is that we have these new customers and we want to learn, or we want to predict directly their uplift, based on their features. So we have learned from existing customers, we want to transform that over new customers, and then we calculate their uplift. And then, finally, we can decide whether we want to target them, yes or no. Right? Because in this case, okay, if we assume that we're profit maximizing, then we want to target Mete and we want to target Daniel because they're giving us some profit. Note that this number might also be negative, but just in this example, it's all positive or zero. Good. And it's important to focus on these two because these will play an important role in the next couple of slides. So this is a simple model predict, as we will get into. So like I said, we can just calculate the profit by summing these two uplift numbers based on our targeting policy, and then we have the profit of our targeting exercise. Good. But usually, firms only have a typical budget to target a certain percentage of customers. We cannot send maybe everybody a certain ad. So for example, we have a budget to only target 30%, then if we're profit maximizing, we only target Mete. So our profit decreases. And further, if we have a budget of 60%, then we can target 2 of the customers, and we have the same budget profit as before. So this is all cool and this is all out there. I maybe hear you thinking, this is all, I know this already. This is all nice, but at the same time, we need to take kind of ownership of privacy. This is because of GDPR and also because of the autoriteitspersoonsgegevens here in the Netherlands. That might kind of slap you on the wrist because you're using the data of customers that might be sensitive. So in this case, I used people's location, but you can imagine that might be way more sensitive features that you could collect or that you could use. That maybe even are highly predictive of this uplift. And I think a good example that I always use is this fine that Meta got for the data that they used. So at the same time, we're using these fancy methods to maximize profits, but at some point also GDPR might come along and slap you on the wrist, and there goes your profits. So is there any value in doing this targeting anymore? So that's why we have to balance that with privacy, is at least my thesis. Okay, like I said, these two components of this table were important. In this presentation, I will focus on one strategy. It's called the DP-CATE, and that refers to the uplift, right? Because uplift is the same as conditional average treatment effect in this case. And the other strategy focuses on this targeting policy. Because kind of intuitively, that's essentially my presentation in one sentence. We're just adding some noise to both of these columns, or one of these columns. But it's a little bit more involved than that. Good. So the first strategy, like I said, focuses on this predicted uplift. So we're talking about the profit that these customers are making. And if we use this strategy, is what we will see, also in the notebook, is that these uplifts shrink a little bit. So it becomes less clear which customers are profitable. So you can imagine that we don't have access to this uplift anymore, right? So we don't know how profitable these customers are. We only have access to this profit in the case which we're using strategy 1. So now the targeting policy might also change, and subsequently also our profit that we're getting from this targeting exercise. Good. So in this case, the profit decreases, right? So that's kind of the cost of privacy that we will see. And the second strategy focuses on the latter column, and it is essentially flipping a coin for each customer. So we have, okay, we're going to target me in this case. Let's say I'm the first customer. Then we're not going to target somebody in this audience, and we're going to target another person from this audience. And now I'm going to give you a coin, and you're going to flip this coin, and based on that outcome, you're going to get targeted, yes or no. That's kind of intuitively what we're doing. So you can imagine that these numbers change, and then also our profit change. Right? So we now only have 500. Good. So you can already see where I'm going is that we have profit in this case, in this exercise. On the y-axis, we have some measure of privacy risk. On the x-axis, and then we have these two strategies that we want to visualize. How profitable are they, and are they competitive compared to not using any privacy protection? And at the same time, I can maybe hear you thinking, what is this privacy risk? How are we going to quantify this? Right? Because this is still a little bit vague. Are we just going to add some noise? Or I talked about throwing a coin, but apparently you can vary this privacy risk because I have a graph. So let's see how we're going to do this. So how to quantify privacy risk. And to quantify privacy risk, I would first like to start with the fundamental law of information recovery. And I promise you it will be short. I have the formal theorem. You can look it up online, and I will just talk about the intuition. The intuition is that giving overly accurate answers to too many questions will inevitably destroy privacy. And yeah, let that take in a little bit. And I will just go to the implications, because it's kind of a repetition, is that given enough analyses, complete reconstruction of individuals. Let that sink in. The intuition is that if you're, for example, calculating a mean, or you're doing OLS, you're always releasing some information about those customers in the data set. You're showing summary statistics in a paper. That's what we academics do. This is all releases some information about these individuals in the data set. And at some point, if we do enough analyses, then we can reconstruct these individuals. For example, what was their age, or where do they live, and all types of stuff. Good. And at the same time, I also think this is a very interesting one, is there is no magic way to completely protect privacy. And this has quite some implications, I think, for the field and also for practice. Just to give some more intuition to these two statements, I always like to use this example. So I'm talking about given enough analysis, complete reconstruction of individuals, and I like to use a puzzle. Because you can see each little puzzle piece as an analysis, let's say calculating a mean or a count from your data set. And if you slowly start putting those analyses together, then at some point you start recognizing what this puzzle is about, right? And it becomes easier and easier. And this is the same way as it happens with privacy risk. So over time, the more analyses come in, it becomes easier, even in an exponential way, according to differential privacy. We will get into that. But it becomes way more clear, and at the end of the day, we know this is Van Gogh. And I think we're also in the same room that has the same name. That's a funny coincidence. And the other one is that there's no magic way to completely protect privacy. And I think this is an important one. So there's the rise of companies that promise you that their data, if you transform it in a certain way, is privacy safe. Right? And I would like to kind of reflect on this. And we have companies in practice that guarantee you that it's, or at least make you a promise that it's privacy safe, synthetic data, for example. But actually, the FLIR tells you that's impossible. So that's kind of a tension that's going on. I think this is a good development in a good direction, but I think we also need to be careful with these promises. And I have a little bit more about this if you want to read up on this in my paper that is published. Cool. So let's look at a little bit of a timeline. So what do we do now? It sounds kind of grim, right? There's no magic way to protect privacy, so what do we do now? It's like I talked about those companies, and what now? Okay. So we have the FLIR, that's kind of, quite a statement. And then Dwork and Roth started to think about this. So, and they were thinking, and they introduced differential privacy. And what differential privacy, its philosophy is that essentially it's counting the puzzle pieces, or counting the privacy risk that releases with every analysis. And if we keep track of that carefully, then we can control and protect the privacy of individuals. Good, I will get more into that later. And it's getting more and more popular because we also see it more in practice. So we see it at Apple, and in previous presentations at this conference, they were also already a good example and more of an introduction to differential privacy. As you can see, the US Census is using it, Apple in their keyword suggestions, LinkedIn, Google, and all kinds of examples. So it's gaining a lot of traction. So like I said, this differential privacy has a kind of a different philosophy towards privacy protection. There's no magic way, but the best that we can do is to control the privacy risk. So essentially counting these puzzle pieces as we lay them. Okay. Besides that, differential privacy is also a mathematical definition of privacy, which makes it nice to work with, I would say. And it gives us this theoretical measurement of privacy risk, and this is epsilon. And a higher parameter of epsilon, or a higher number of epsilon, implies higher privacy risk. And this is important for subsequent slides, because we will use this inside of targeting exercises. A very strong property of differential privacy is that one set, so we do our analysis, we satisfy a certain number of epsilon. It's important it's impossible, I was struggling to find the word, it's impossible to increase this epsilon. So that's also a very strong property. Another property is that any function can satisfy this epsilon. So that's also hopeful, right? That we can do any analysis, and for any analysis, at least theoretically, we can satisfy a number of epsilon. So we can calculate the mean, we can do linear regression, we can do targeting in this case. Good. So we get this big button, and that's epsilon, and we can turn it. So we can make epsilon very high, or we can make epsilon very low. And if we make epsilon very low, then there's less privacy risk, so more privacy protection. And that's what you get with this button. Okay, so we have now this theoretical idea of differential privacy. Let's put it in an example of targeting in this case. Right, I've showed you this targeting policy, and in this case, I just have a bunch of customers, 5 in total, I believe. And then I don't target a lot of customers, I only target one. Right, and just assume that this is the profit maximizing targeting policy. So what I'm saying is that the customers that are not getting targeted may have negative uplift or 0 uplift. And the one that we do target has positive uplift. So that's what I'm saying with profit maximizing. And then we randomize this essentially column or vector to carefully satisfy an epsilon. Cool. So we do that, and there's a math behind this, which I will show later in this presentation. And we kind of get a different protected targeting policy. So this targeting exercise now satisfies a certain epsilon. Okay. Cool. And we can do that. So remember that the ground truth was that the profit maximizing policy was that we target 20% of the customers. So I have a red line here on this graph. And on the x-axis, I have epsilon. And this ranges from 0.01 until 10. And you can see that at very strong privacy protection or very low privacy risk, that we're essentially doing a random coin flip, right? We're essentially, because it's 50% chance of getting targeted. So that's the same as just giving every customer a coin and then saying, based on if you land on heads, then you're getting targeted. But you can also imagine that this doesn't allow you to get a lot of profits, right? Because it's just random. We might as well throw up a billboard. Okay. But you can see as well that as soon as epsilon increases, that kind of in this shape, we get closer to the profit maximizing policy, but this is only at epsilon 10. So this kind of gives you a feeling for which epsilon levels are relevant in practice, I think. Yeah. So yeah, the targeting policy is approximately the same. Okay, so back to this trade-off. I asked out loud, okay, what about privacy risk? So here we have epsilon, and we can use it to vary this privacy risk in this case. Cool. Now I can imagine that you're curious about the private targeting strategies. So we're now getting into these. So that was kind of an introduction to these strategies. Oh yeah, there was a bit of lag. Let me get back. Perfect. Okay, so again, the same example. I'm going to click it here. And we're using, in this case, the DP CATE. So the important thing to notice is that we're again focusing on this uplift, right, on this money that we're getting from customers. And as I mentioned in the introduction, the whole core idea of this strategy is to estimate the causal effect of an ad in this case. And preferably that we would like to know the impact of this ad before we're targeting any customers, because then we can sort the customers based on their uplift and then maximize profits. Okay. However, note that I said in a causal way. So we want to estimate the causal effect, but usually, you know, these features, these customers, they live in a complex environment. This is kind of a statement. But you might have like ads running at the same time. You might have different stuff going on. I don't know. And it's pretty difficult to really isolate this effect of only this ad on money, because that's what we're interested in, right? And one tool to use this is double-debiased machine learning. And I have an example of how this works in the notebook. I won't get into too much technical details. There are people that can do that way better than I can and have done already online. So I would just refer you to that link that I have here on this slide. And instead, I have prepared a notebook where I demonstrate how this double-debiased machine learning works, at least the intuition. Okay, so first we're just going to simulate some data. So I have done this. I have this function somewhere in the library, and we're just going to simulate some covariates. So here we have covariate 1 until 6, and what we also generate is their spend. So really the causal effect of an ad, and we kind of simulate what's going on in the environment. And then, at the end of the day, we get this causal effect. So we know the causal effect of a discount coupon in this case. Oh, should not double click. We have which customers are treated, right? We have the sales. That's what a company typically observes. And then we have their customer behavior, also what the company observes, of course. And so on average, at least the ground truth is that this customer spends about 93 cents on average based on an ad. I would say that's quite, I don't know, realistic, I would say at least. And if we look at this vector specifically, then it's the same that I showed you in the slides. So here we can see that customer 1 or 0 has 60 cents that it will spend if we show them an ad. And our goal is to recover this number, right, for all of these customers. Okay, cool. So I can also demonstrate what it looks like when I plot this distribution. So you see, oh man, this is really... Okay. So you can see that most of the customers, they spend a positive number, right? But there are also some customers that spend less because of this ad. Okay. So then moving on is what double-D biased machine learning does, is that first it learns the probability that a customer is treated. So you set up a random forest, and you kind of learn based on X, the targeting indicator for each customer. You learn what is the probability that they're being treated, and you subtract it from the actual treatment. Okay. This is just details that you can look up after the presentation if you would like. And we do the same for the outcome, so for the sales. And the intuition behind this exercise is that we want to isolate this effect of only this ad. So that's the kind of the intuition. And then step 3, we're learning the treatment effect function. So what I had in the introduction, right? We're learning a mapping from the features onto the uplift. Okay, so that's what I do here. And then at the end of the day, we get an estimate of, so note that this is a tau estimate, and we get an average treatment effect of 0.96. So that's, I would say, close to what we observed, or what's the ground truth. And again, if we compare this to the truth, so the blue line is the truth, then we can see, okay, it's quite accurate in this case. But note that this is quite a simple data generating process, so the environment in which the customers live is quite simple, that I've simulated here. But we can also calculate the profit. And remember that I talked in my introduction about we sort the customers based on their uplift, what they're expected to spend, and we have a percentage of customers that we can target, right? So we have a budget as a firm. So the budget here is on the x-axis, and the profits is on the y-axis. And it's pretty clear that, you know, these estimates, they cause you to lose a little bit of profit, right? Because the profits by the estimates is the black line, and the red line is the true profit. So this is really the optimal profit that we can get from this targeting exercise. Cool. So let's get back to the slides. So this is essentially how DML works. But now we use a little bit more of a sophisticated method in my case. So in my library, I use, or I guess, I use a neural network to represent this treatment effect function. So in the example, I used a random forest. And the reason is that there are libraries out there that help you satisfy epsilon using training neural networks. So this is very nice. So we essentially can vary we essentially can vary the privacy risk from differential privacy using these libraries, and that gives us a kind of a measure of the privacy risk. And the intuition is that these DPSTG is in this case, so it's a differentially private version of stochastic gradient descent. It limits the contribution of each individual to the neural network, and does that in a very clever way, and that's in the paper that I reference here. But let's get back to the notebook. So in this Python function, I first start with defining noise multipliers. And these noise multipliers, they're essentially what type of privacy or how much noise are you adding. So what epsilon do you want to satisfy? And the larger the noise multipliers, the lower the privacy risk. So the more protection you're adding. And then I kind of loop over these noise multipliers. I create a directory because it's saving checkpoints during training. And then I have this function, strategy 1, PCNN, and what it requires, it gives you a whole lot. So note this is a project in progress. It's work in development. And I'm feeding it this vector of covariates, the sales, the treatment, whether we target them, yes or no. And then I specify batch size, just as we normally do with neural networks, epochs. It's all there. And then we do some fine-tuning in the background. That's when I'm specifying max epoch, so that it kind of gives you how long is this neural network training, or do you give it time to tune? We create a directory, and this is where we fill the noise multiplier to satisfy an epsilon, so satisfy privacy, and we set a seed for so that we can get the same results the next time we run it. Then we save this, And I think the output is a little bit more interesting, I guess. So DPSTG gives you this nice overview of what type of epsilon are you satisfying, and in this case we're looking at this line, and we see that epsilon is 0.05 here in this case. So that's what you're getting back, and you get a lot of feedback still, so the optimal architecture of the neural network. And the interesting point is to focus on this because it's giving you back the average treatment effect, right? And how much heterogeneity is in these customers. So is there a lot of differences among customers in terms of their spending? And as you can see that there is some bias. So in this case, we had epsilon 0.05, which is very strong privacy protection. So that means that we also have to, that loses some accuracy, right? That's what I said with this big button. So the lower we, the more noise we add, the less accurate our targeting algorithm is going to be. And we now kind of get a sense of how less accurate. So in this case, I am a little bit less strict. So in this case, epsilon is 1. And then we get, it's clear that the average treatment effect is way closer to the actual truth, right? So the profit will also be higher. So let me skip these. So if we compare them in terms of their distribution, then the density, then you see that at epsilon 1, the dashed line is the truth. And you see that at epsilon 1, it's pretty similar to the truth. So I guess we're not losing a lot of money if we use epsilon 1. But for epsilon 0.05, we see a completely different effect. We see that the density of the distribution is shrink. So that means that it's kind of the example that I gave earlier on, right? With the table and where we had big money, like 5,500, and then when we added privacy, these numbers become smaller. So that's what's going on here. It's less clear which customers are profitable and which aren't. So it becomes harder to disentangle these customers from each other when we add privacy. So if we look at the profit, I've added a random sampling, just picking random customers to this plot. So you see that the purple line is the random selecting, so essentially this coin, so you could also call it epsilon 0, I guess. And then I've added these two privacy protection targeting algorithms, I guess, private targeting strategies. I'm still struggling to find the terminology for this project. So we have epsilon 0.05 and we have epsilon 1. And you can see that in this case it's pretty okay, that we're not losing that much profit, right? The lines are not that separate. So in this case we can have both privacy and at the same time profits. But I would be happy if this was really the truth, but in reality we have to, the data is way more complex, so you won't have this nice profit graph, unfortunately. But in this case, the covariates are just normal distribution, so that's pretty nice. Or simple, at least, to learn for the neural network. Okay, perfect. Then looking at strategy 2, I mentioned that we focused on the second column. So now we've covered the predicted uplift. We're looking at the second column, and then these zeros and ones are changing in a certain way. So this is a relatively simple strategy, is that we flip the targeting decision with a probability that is very carefully set to satisfy epsilon. And there's a proof in the paper that I can talk about after the presentation, or maybe share the paper. But looking at these customers, we keep the same targeting decision with this probability, and we change the targeting decision with the probability here. And it's so simple that we can simply set epsilon to 0.05, fill in this formula, and then we get our probabilities, and that's the strategy. And the proof is in the paper why it satisfies, and I also have we're also working on a derivation of what is a privacy elasticity of profits. So let's say you would increase your profits with 1%. What is the, let's say you would increase your privacy risk with 1%. What would be the effect on your profit? But this is still work in progress. Okay, let me get to the notebook. This is you might as well program it yourself, almost, I would say, to be honest. But this is a function that I've created. And it bootstraps, because you might be interested in confidence intervals in this first argument. And it takes two arguments, so the truth, the real uplift, or the real CATE. In this case, we have it, but you might not have it, so you could use your estimates also in this argument. And the estimates, which we have. Remember, we created them in way back. Then we want to specify the budget that we have, so 5% until 100%, and then we vary that, and we want to specify the privacy risk that we're satisfied with. And again, that we can reproduce the outcome, then it starts running. Okay, very nice. And then we can kind of, I hope that, let me zoom back. Then we can kind of compare these two strategies. So we both now have the profit for our first strategy. Remember, that's the 2 lines very close to the true profit. And we have our first strategy and our random policy. That's flipping the coin. And we can see now that in this case, strategy 1, or the DP CATE, is actually performing way better than or strategy 2, I should say, or DP policy. And that's the reason is essentially because this DGP is very simple. But back to the slides. It's a nice hint for me. But we do a more complex simulation study as well, luckily. So we benchmark both strategies. We assume 10,000 customers and a nonlinear treatment effect function. We run both strategies 100 times to get confidence intervals with these privacy risk levels and also without privacy protection. And we calculate the profit, just a reminder, sorting the customers based on their uplift and then summing based on their true uplift. So not their estimate. So we're only doing the sorting by their estimates and calculating the profit by their true profit, because that's then the true profit we would have get if we would have applied this in practice. Okay, so this is kind of the result of the real data. So this is simulated. This is the optimal profit that we would have. And then here on the x-axis, we have again the top percent targeted, or our budget, or the amount of customers we can target. And then we have our profit in euros on the y-axis. And then we have our 2 strategies with 2 different colors. Okay, let me move on to the next slide. So in this case, I'm varying the privacy risk as well. So we have the real data. We have the data without privacy protection. So you can see that they're very close, right? These 2. So it kind of gives you optimal profit, at least in this case. I've also added a random policy. That's this dashed line. And you can see that for these privacy risk levels, for epsilon 5 until epsilon 0.05, that the DP CATE, the first strategy that I talked about, is essentially random. So that's kind of trouble. So when I first saw these results, I was like, okay, well, that's interesting, but we will get back to it. And the DP policy kind of gives you a reliable, or at least more profit over the other strategy. So this was really interesting to me, is that apparently it matters how you implement differential privacy. I mean, I kind of knew that, but not in such a big way. Then I thought, oh, well, let's increase the sample size. So I increased the sample size to 100,000 to 1 million customers. And these are essentially the same results. And what we see here in the middle for 100,000 is that this DP CATE is getting closer to the second strategy. So it's performing better. So it's getting closer to the second strategy. And even for very low privacy risk, and this is what we would rather have, right? We want to have low privacy risk and high profits at the same time, preferably. The DP CATE is outperforming the other, at least. Essentially, they're quite the same, but for a larger sample size, even larger, for 1 million customers, it's outperforming the other strategy. So it turns out that the circumstances in which you use these strategies are super important to get profit. Yep. Let's see. So yeah, I increased the sample size, and I calculated the profit per sample size. So that kind of concludes my presentation. Is the main insights are, I hope, that there is no magic way to protect privacy, and that we really need differential privacy to quantify the privacy risk that we are working in. And this epsilon is a parameter that we can use to talk about privacy risk with policymakers. So imagine that you would have a conversation with autoriteitspersoonsgegevens or with people from the European Commission. Then you can say, look, I have a proof and it satisfies a certain epsilon. That's better than just saying, yeah, we're just adding some noise. So then you can have a much clearer discussion with policymakers. And also what is very clear from this presentation, I hope, is that it really matters where you implement differential privacy. So the location at which you implement it gives you different profits. And at the end of the day, we proposed these 2 targeting strategies. We created a Python function that mathematically guarantees this protection and allows for profits. So thank you for your attention, and I'm happy to chat after the presentation.
Thank you so much, Gilian, for the wonderful presentation. Now we're going to take some questions from the audience. We have about 10 to 15 minutes for questions. So, yes, any questions? Yes.
Okay. Thanks a lot for your very nice presentation. I'd actually have a question about the last claim that you make on the last slide. Yeah, so this says mathematically guarantee privacy protection. I was wondering if I would be, let's say, a business stakeholder, then all this math I don't understand. How would you kind of practically prove that it also works?
Yeah.
It's maybe a tough question. But
That's a very good question. Thank you. Yeah, that's a very big problem, I think, still with differential privacy, and I think it's still a little bit in development. So I think at least in the academic world, we need a lot of work on how can we translate this epsilon in something that is really intuitive, I would say, in my opinion. So I think there's just a lot of work to be done there to really convince people that it is a mathematical proof and how that exactly works. So I think there's a lot of work to be done for the community to get to a level that we can simply explain, okay, this is epsilon, and if you do it in this way, then that it becomes more intuitive. I hope that answers your question. Okay, thank you.
Thanks for your presentation. I wonder which next steps you would like to take. Are there other more sophisticated techniques? So I know that there is always room for improvement. So what are your thoughts?
Yes, thank you. Yes, for now, the next steps are for me to focus on these two methods. And what I think is nice about the second strategy is that it's so simple, at least in terms of math. And we're working on to get this privacy risk elasticity of profits. And this is, I think, also maybe answering a little bit, I hope, your previous question. This gives you the simple insight that if you increase epsilon with 1%, how much euros is this going to cost me in a targeting exercise? So I think I'm very excited about that, personally. I hope my team also is. Yeah, so this is kind of the next step. And other than that, yeah, there are a bunch of locations that you can still add or satisfy differential privacy, maybe during data collection. Maybe you can transform your existing data set under a certain epsilon, shuffle it, for example. There are all kinds of ways, and I think it would be very interesting to see what type of profits do you get when you satisfy differential privacy here. So this is also maybe what I would like to look into later. Yeah, thank you.
Yeah, thanks. Well, you kind of already answered my question, I suppose. But as you've shown, there seems to be a clear trade-off between the amount of noise that you introduce and the profits, right? So would you suggest, is there any kind of strategy where we can determine the correct threshold for a company or for a use case, determining that amount of noise that we want to introduce?
Yeah, thank you. The amount of noise that you add directly has an impact on epsilon. And there are a bunch of ways to add noise to, let's say, a neural network. You could do it at the weights, you could do it at the gradients, you could do it at the data, the input, at the labels. And I think that it really depends on where you add this noise, how much profit you're going to get, and where you add it is super important. There are a bunch of papers that show that if you add it to the gradient, like in this paper that I'm using, then you can get way more utility, is what they call it in the paper itself. So there's a lot of research to be done in this field, I think.
Yeah, thanks for the presentation again. This is quite an interesting statement that you make, where there's no way to completely protect privacy. There have been certain talks during this conference where some people have talked about encrypting data, encrypting the machine learning models itself. Do you think that encrypting data itself doesn't necessarily protect privacy?
I think that's, you're right that this is a very bold statement. And I think that I know too little of those methods to really make a statement about that. So about you're referring to encryption and all these methods. And what I'm essentially referring to is that in practice we're kind of just adding some noise and then saying, okay, this is privacy or this is private. So I would have to look into that, to be honest, is the honest answer. Yeah.
Yeah, thanks a lot for the talk. I was also really surprised with the simulation result you shown, as I guess you were, because my intuition would be that, you know, if you're adding some noise to the profits, like very profitable customer will remain profitable, even if the predicted value is not exactly the same. Do you think it might be a kind of conceptual instance of kind of overfitting because, like, if you don't have enough samples, like the method is too complex to actually fit if you add some noise on top of that, and that could explain some of the results you've shown?
Yes, I think yes, I think that could be one explanation indeed. That it's kind of a regularization that we're adding to this neural network. We're adding noise to gradients. Not exactly how that formally compares to any other methods that we're already using in regularization, but it's definitely helping. I mean, if you're not adding too much noise, I guess. But it is kind of an intuitive explanation for why we could still have profits. And I think there are even papers about that they're showing that it's similar to regularization and that it works in a similar way, that it becomes more difficult to overfit, essentially. I hope that answers your question.
Cool. Thanks for the great presentation and talk. So my question is, do you have any thoughts on if there could be a positive feedback? Because you mentioned you run quite complex simulations on customer behavior. So do you think there could be an outer loop as well? Because, I mean, the situation that you have privacy might drive more customer flow. I mean, for example, there might be a website where if customers know that, I mean, privacy is being taken well care of, there might be more customer flow and in turn lead to more profit. So do you have an opinion or any thoughts on such an outer loop?
So you're saying that, let me help me please to understand. So you're saying that if you have a company that focuses on privacy, then that would add more customers and in that way you're getting more profit, or is that?
Yeah, exactly. I mean, so this is now sort of a per customer profit. Like the profit you mentioned, y-axis, is sort of a per customer profit, but then you might also think that the very situation that there is privacy awareness might drive more customer flow and in turn more profit.
Yeah, definitely. At least that's my intuition as well. But I think that we also at some point, I'm very interested in formally testing this at some point, that we, for example, use these methods in an email campaign and that we communicate that we're protecting their privacy in some way, or at least adopting differential privacy. Yeah, we really have to carefully think about the formulation, maybe with Nutri-Score labels in terms, but then in privacy form, I don't know. It's just some speculation, but I could definitely see that in the end, if you start adopting these strategies, that maybe more privacy-sensitive customers are more willing to spend more at your company, perhaps. Yeah. But yeah, let's see. I mean, and this is something that we have to study, I think, first to make any statements. I'm not aware of any papers, at least. Okay.
One question.
Yes.
Thank you for the presentation. I want to ask if there is any way to estimate epsilon for existing data sets or model which we have already have.
Yeah, thank you for the question. We actually made a privacy attack in the paper that I showed or developed. Let me go back. In the paper that I kind of threw in there. Damn, it's long. Okay. Yeah, in this paper, what we're doing is that we have an existing data set and we want to transform it into something that is privacy friendly. And the title, the Where is Waldo, is coming from that if you have a larger data set, that means that you're able to put epsilon lower. But that's not answering your question. To answer your question, as soon as you have a privacy-friendly data set, then the privacy attack that we develop in this paper allows you to estimate epsilon. And this relates to the true positive rate, false positive rate, and divide them, and then the log, something like that. But more than happy to talk about this after the talk. Thanks.
Are there any more questions from the room?
Yeah, thanks a lot for your presentation. So you were saying that by doing more analyses, you're able to put down the puzzle, basically. Don't you believe that for very large companies, adding some additional randomness just results in them still being able to come to the final puzzle because they do so many analyses?
Yes. So what you're saying is, or suggesting, is that if you do a lot of analyses and then add some noise, that you're still be able to see that this is a Van Gogh painting in the end. Yes, that is true, but so that's also what they show in the FLIR paper, where they develop it. Even if you add some noise, then you're still able to reconstruct. But that's differential privacy kind of counts the number of analyses so that you're doing, and then also takes into account the noise that you're adding. So it really, and then mathematically, it calculates this epsilon. So it's kind of a different philosophy. So you're right that if you just add some noise and just keep doing this, then at the end of the day, you will still see the Van Gogh. But differential privacy kind of, I need to be careful when saying this, but I hope that that at a certain point it will not allow you to make this puzzle any further, right? So that's where, if you have epsilon 5, then you might complete it a little bit longer. You might add some more puzzle pieces. But if you have 0.01 epsilon, then you're only allowed to do this, for example. And then it becomes much harder. So that's kind of the intuition. Does that help?
But don't you then at some point come to random flips for companies that are large enough, basically?
So what we see, and also in our paper, is that if the company is very large, then it's actually very easy to, where is this paper? Anyways, that it's actually very easy if you're, or not very easy, it's more easy if you're a large company and you have a lot of data to add noise, because if you have a larger sample, then the noise kind of more cancels out. So that's kind of what we see in, empirically.
Okay, thanks.
If there are no more questions, we're going to go into a break now before the next session. The next session will be at 11:05, so feel free to wander until then.